Hey there, chemists. In this video, we're going to look at how we make carboxylic acids. And I'm going to start us off with just some common carboxylic acids on your notes. This is benzoic acid, when you have a carboxylic acid attached to a benzene. The main component of vinegar is acetic acid. Actually, the main component of vinegar is water, but there's 5% acetic acid in vinegar. Most of you have certainly tasted the next one. This is a tricarboxylic acid called citric acid. It has 3 acidic carboxylic acid groups and a tertiary alcohol. And the last one actually isn't a carboxylic acid, it's a per-carboxylic acid. This is a familiar molecule to all of us. This is called Chloro, Peroxy, Benzoic Acid. Just as a reminder of a reagent you've seen before, and hopefully you're saying to yourself, yeah, that's MCPBA, which you've seen to turn alkenes into epoxides, and more recently how to make ketones become esters via the Baeyer-Villiger oxidation. So those are just some common acids that every chemist kind of should be able to recognize. At the top of that, or right below that I should say, are some review reactions that in theory we already know that make carboxylic acids. That's a theme of today. How do we make carboxylic acids? So I want you to actually hit pause and see if you can dig into your notes and find the reagents that you would use to do these 4 reactions. Hit pause right now and see if you can do that. Okay, if you've done that, the first one, the oxidation of a primary alcohol, that's the Jones oxidation, which is with chromium oxide and water, specific for primary alcohols. You keep all your carbons, but you oxidize the alcohol first to an aldehyde and then a hydrate under aqueous conditions, and then it becomes the acid. Right below that, we actually lose a carbon in the oxidative cleavage. This is KMNO4. And the carbon that we lose from a terminal alkene becomes a carbon dioxide. So there's still atom economy here. You keep all your carbons, they're just now separated. What about cleavage of an alkyne? Cleavage of an alkyne, we learned ozonolysis in the presence of something like water. Every carbon in the ozonolysis of an alkyne becomes a carboxylic acid. That's different from ozonolysis of alkenes, which gives you aldehydes and ketones. Alkynes give you carboxylic acids. The last one is very specific for benzylic carbons. If you have a benzylic carbon group, it doesn't matter what is attached to this thing as long as there's a CH2. If you treat this with KMNO4, you get specifically a benzoic acid. So this specifically makes a benzoic acid. So it's more specific, but it still counts as a synthesis of an acid. Okay, so now let's look at some new ways that we can make carboxylic acids from other functional groups. The first one I think is the easiest one to understand in terms of the mechanism. It involves a Grignard, which you know how to make from bromides. It's the treatment of a Grignard with carbon dioxide, CO2, followed by an acidic workup, H+. Notice that it adds a carbon. So we start with a 2-carbon Grignard in this example, and we make a 3-carbon carboxylic acid. To show this, let's redraw our Grignard. And let's actually draw out a carbon dioxide molecule. Grignards are nucleophilic at the carbon attached to the metal. So I'm going to draw an arrow from that carbon to the carbon in carbon dioxide. And carbon dioxide we can think of as containing a carbonyl. So draw a second arrow with that pi bond going up to the oxygen. That'll give you an intermediate with 2 carbons now attached to the carbon that used to be CO2. It's still doubly bonded to one oxygen, but it's singly bonded to another, and there's a negative charge. This is called a carboxylate. That's the conjugate base of a carboxylic acid. And here's where the Grignard has done its job. This oxygen anion is coordinated to the magnesium bromide ion that's from the original organometallic, hence the need for an aqueous workup. So to finish the mechanism, you simply protonate the carboxylate, and that's how you get your acid. Very short mechanism, just 2 steps. This is a reminder of why we can't carry acidic functional groups in the presence of a Grignard. Grignards react with so many things. It's really hard to carry a functional group in a Grignard. We're pretty limited to just hydrocarbons, alkanes, alkenes, alkynes. Those are what you can already have in the Grignard. Nothing other than that for the most part. Okay, the other three reactions for today are all based on starting with a carboxylic acid derivative. We have an acid chloride, an ester, and an amide. And these are all functional groups we don't really know how to make yet, but they're all useful in that they make carboxylic acids. Starting with acid chlorides are the most reactive of these functional groups. We'll study them in the next few lessons, but for now, let's see how they react to make an acid. They're so reactive that just water will react with them very readily. Acid chlorides fume in the presence of the air most of the time because there's enough moisture just in the air in most environments to do this type of reaction, where water adds to the acid chloride, you get a new oxygen attached to that carbon. There's now a plus charge on that oxygen. Notice the chloride does not leave right away. You do not have an SN2 substitution. This is an sp2 carbon. The oxygen absorbs that electron density. It's more electronegative. There's a strong dipole going toward that oxygen, so the carbonyl goes up. However, the carbonyl comes right back down in a second step, and now the chlorine leaves. This is a two-step mechanism via that tetrahedral intermediate. And now we get what looks like the protonated version of your acid. So we can use a second water molecule to just take that extra proton away. And that's how you get your carboxylic acid, which means you generate an equivalent of hydronium and chloride. Hence, you sort of have HCl, which could off-gas when you're doing this chemistry if it's not in water. It can happen, or if it's in only a stoichiometric amount of water. Hence why some carboxylic acids look like they fume in the presence of just air because of off-gassing HCl. Okay, the next one is the reaction of an ester. This is used in soap making, used to make soap. Soaps are historically made from fats, which contain triglycerides, which are 3 esters. We're going to show it with just 1. And esters are also reactive at the carbonyl. So if I draw out this ethyl ester, I'm just going to abbreviate the group on the oxygen as an ET. Saponification is how we turn these into acids. It's 2 steps, base followed by acid in a second step. We really have to put these numbers here to show that it's not mixed together, obviously. That would just be water. So in the presence of hydroxide, the carbonyl gets attacked, and the carbonyl absorbs those electrons. You get a negative charge on the oxygen, you get a new OH, and an O-ethyl. And something very similar to the previous mechanism occurs. The oxygen anion comes back down, it actually kicks out the ethoxide. We're under such basic conditions that the ethoxide can act as a leaving group in that step. You might think that you're done. Oh, there's the carboxylic acid. But you are actually not done, because in the presence of the group that we just left, the ethoxide, the conjugate base of ethanol, a very fast reaction happens. You guessed it, it's an acid base. And we actually first make a carboxylate. And your byproduct would be ethanol. And a good Orgo 1 reminder of why this occurs: the pKa of a carboxylic acid, roughly 5. pKa of an alcohol, roughly 16. Higher pKa means weaker, aka more stable, aka if this reaction is reversible at all, the equilibrium lies very far to the right-hand side toward the carboxylate. Hence the need for step 2. Step 2 is H+, and it's very fast. The carboxylate simply protonates, and that's how we get our carboxylic acid. So the saponification is really just the formation of a carboxylate, and that is sort of a soap molecule. Historically, soaps are made of carboxylates. Nowadays, detergents are coming from sulfonates, conjugate bases of sulfonic acids, but historically, you can still make soaps in this fashion. Okay, there's one left. It comes from the hydrolysis of an amide. That means the amide reacts with acid. That means we're only in positive charge, and we somehow have to get this nitrogen group to leave. I want you to think of H3O plus as the combination of H plus and water. And since you've seen a couple of chemistry, a couple of reactions in this unit that have shown us how to make acids, I want you to hit pause one more time and see if you can figure out how this mechanism works. Take a few minutes and see if you can figure out a little bit of this one. I'll give you a hint. The first step is protonation of the carbonyl. So your intermediate is actually an oxonium ion with a plus charge on the oxygen. And now I want you to hit pause and see what you think happens next. Okay, well, we used up H+, so now water is going to have a role and attack the oxonium carbon and send those electrons up. That's how we get a second oxygen on that carbon. The first few steps in any mechanism are really the most important. If you go down the wrong path in a mechanism, it's really hard to backtrack out of it. So hopefully at least you got the first few steps right, because then it will be easier and easier as you go on. When we're here, I'm not really sure where to go next perhaps, so I look at the product. I realize I need to make a new carbon-oxygen double bond, and I realize this nitrogen group has to leave. We're in acid, so I'm not going to have this nitrogen group leave yet. So that means I need to put a proton on it. So let's do an acid-base reaction. We'll just write H plus transfer as an abbreviation. In all likelihood, this happens with solvents intermolecularly. I'm going to show it intramolecularly, where the nitrogen takes the H from where I have too many and puts it on the nitrogen itself. Now I have a positively charged nitrogen group, and now that nitrogen group can leave. And it's facilitated in leaving by the neighboring oxygen, either of the neighboring oxygens. And if you draw the product of that, you get effectively the protonated version of your product. So we're one step away. We just kicked out methylamine, so we can use that as a base to take away that last H, and that's how we get our product. So, just like most acid catalyzed mechanisms, our first step is adding an H+, our last step is taking away H+. You know you're on the right track if you're doing things like that. So these are just a couple of new ways to make carboxylic acids, and some reminders of old ways, and in the next lesson we'll look at how we can make carboxylic acid derivatives and do reactions with those.